Transportation. How do you get around? A lot of the information from this talk came from several talks that were presented at the Physics of Sustainable Energy Conference in Berkeley in 2008. This is Alex Farrell, who talked about different fuels for cars. Mark Duvall from EPRI gave a great talk on hybrid electric vehicles. Tom Wenzel from LBNL talked about the relationship between vehicle size and safety. And Venkat Srinivasan talked about batteries. So you're at the cocktail party, and someone says, I'm not going to buy a more fuel-efficient vehicle because I'm concerned about the energy that's used in order to make a new vehicle. This is called the embodied energy. But the embodied energy of your car constitutes a very small portion of the full carbon footprint of your automobile, 90% or so being due to the burning of gas. This is usually the case for all energy converting technologies such as a light bulb or a heater or a motor. And the analysis shows here that the embodied energy is about equivalent to 1 year's worth of driving. That is, unless you drive very, very little. Most people drive on the order of 15,000 miles a year. So what this means is if you drive at all, investing in a fuel-efficient car is going to reduce your carbon footprint. So what this graph shows, it turns out that most people spend the same amount of time commuting, no matter how rich they are and how fast they commute. If you have more money, you just commute a greater distance. This is the per capita income per year. This is the annual per capita kilometers traveled. And so very poor people walk for 2 hours a day, and very, very rich people may fly in an airplane 2 hours a day. Let's say we want to change the fleet to more economic cars. And when I say fleet, I mean the cars everyone is driving. In an interest to do this, it's important for us to know how long people use their cars. And so this is the age of the car, and this is the probability that it'll still exist. However, this is the relative use, so as a car gets older, people use it less. When you multiply these two curves together, you get this, which is the relative miles traveled. So although the average car lives for about 18 years, its productive lifetime is about 11 years only. So if we want to get everyone to use electric cars, we're going to presume it's going to take about 11 years for most people to start using a different car. Okay, so let's take a look at some technologies. What do we know about fossil fuels? Well established, works great. The resource base is large but dwindling, and there are a lot of environmental effects as we try to get that harder to get oil. This is where it all is. Most of it's in the Middle East, unless we consider the tar sands in North America, up here in Alberta. We've used about half the accessible oil. We can extract oil that's more and more difficult to get to by using fracking, for instance. It just costs more, and it also costs more in the environment. Where we can see tar sands, the upstream emissions is more than half the emissions due to burning the petroleum after you've refined it. The United States could do to improve the efficiency of the automobiles on the road. And we see this is starting to happen in California, and the United States has since picked up since Obama was elected. Then you ask yourselves, well, if we don't make efficient cars, what are we putting our energy and time into? And we can see here the green curve represents the relative miles per gallon. All of these graphs start at 1 as just a relative term. So we can see the fuel efficiency improved greatly around 1980 and then leveled off and actually even dropped. So where did all that technological innovation go? Well, we improved the horsepower, we made the vehicles bigger, and we made them accelerate faster. And so if we want to, we can make much more efficient vehicles if we don't worry about being a muscle car, if the performance and the horsepower are less and the weight is less. But what about safety? You know, I'm going to get hit by a car, and if I have a light car, I'll die. This talk was very interesting, where we look at the probability of a fatality per year depending on the car. This is the probability of the driver of the car being killed. This is the probability of the driver of the other car being killed. So this is the very good direction where no one dies. This is a bad direction. When you're up here, you're driving a vehicle that kills other people, but you're safe. And what's interesting is 1-ton pickups are just plain bad. They're bad for you and they're bad for the other driver. And we investigate, why is this so? Most of the deaths are not actually due to acceleration, but because you actually get impaled by the frame, that these penetrate the other vehicle. What's interesting is the Dodge Ram. This is the frame. And so take a minute and try to find your own car here. And then you ask yourself, well, if driver safety doesn't correspond to the weight of the vehicle, what does it correspond to? And it turns out it corresponds to the quality of the car. And how they measure the quality of the car is they look at how much is your car worth after 5 years. So mint your 1980 car if you wanted to buy it in 2003. So these cars are just better made, kind of supporting the idea that the easiest way to not be killed in a car accident is to not be in one to begin with. So you need to store energy to drive a car because cars require quite a bit of energy. And generally we've relied on liquid fuels. But batteries give us the ability to use electric motors, which are much more efficient with the use of energy than the internal combustion engine. There are 3 different kinds of batteries that we'll look at real quick here. This is how the batteries stack up against each other. The lithium-ion battery stands out for a number of reasons. 1, it has considerably more energy density than the other 2, but costs 10 times as much as the lead-acid battery. Although it doesn't last as long, we can have more cycles of charge and discharge before the battery's dead. Lastly, it's interesting because there are many different reactions that can be associated with a lithium-ion battery. A mobile lithium-ion that can move between the negative and the positive terminals. It has a lower energy state in a carbon matrix than it does in any number of compounds on the positive plate. Let's take a look. Here the lithium is incorporated in this compound, but can break down, releasing the electron and move through this electrolyte to become incorporated in a lower energy state with the carbon compound. The electron is not free to move through this electrolyte, and therefore accumulates on this electrode and becomes negative. When we connect that up, we can drive current through a motor, for instance. It's rechargeable by means of driving the electrons backwards through a larger voltage, making this plate extra negative that will attract the lithium ions back again. Thin, we want all these layers to be very thin and this to be very large, this surface area. And we take that film and we roll it up like a fruit roll, and our lithium-ion battery is a cylinder. If it's very thin, we can have a large surface area which allows a lot of current flow. The danger then, of course, is when the separator gets very thin, we can have a short between the two, which will destroy our battery in the end. That's ultimately what kills your lithium-ion battery. The energy density of the lithium-ion battery has been growing over the years and has a theoretical energy density of about twice what we're achieving presently. We see the cost of the lithium-ion battery has been dropping and is presently equal to that of the NiCad and the nickel metal hydride. Here we can compare our different kinds of batteries. We can compare specific energy and the specific power. The specific energy is the energy density, which determines how far you can drive. The specific power tells you how quickly you can draw power from the battery, which will determine your performance at any given time. We can see lithium-ion batteries are considerably better than any other battery, but not close to that of liquid fuels. Before Steve Chu was the energy secretary, he ran Berkeley National Laboratories in Berkeley, whose mission already was very focused on energy conservation. But he began a focus on liquid fuels, so he had a very strong interest in liquid fuels. He gave a first talk during the energy conference in 2008 and began with this slide, showing the volumetric energy density in megajoules per liter and the energy density in megajoules per kilogram. And so what we see is, for instance, hydrogen has no energy density per unit volume because it's a gas, but it has very high energy density per unit mass. And so it would be great if we could compress it, but it's difficult. More about that later. In any case, we start out with liquid fuels winning the game with a very, very high energy density on both levels as far as how much energy you could put in your gas tank. You can't beat them. And then showed batteries, barely distinguishable from the origin. When he showed this, everyone laughed, and he said, so you can see we can't really count on batteries to drive our vehicles. And it took me a while to realize why I was very angry with this. And ultimately it was because it is very misleading. And so we did some research and published a paper addressing the issue of energy density. Because your thermal energy density is the amount of energy stored, how much heat you can generate per mass of fuel. But you can't drive a battery and you can't drive a gallon of gas. You have to convert that thermal energy into mechanical energy, and you're going to need an engine to do it. So you need to multiply by the efficiency of electrical conversion. Furthermore, it's not just the mass of the fuel you have to carry around, but you have to carry around the whole engine and transmission. The reason this is important is because the conversion efficiency for the internal combustion engine is 10 to 20%, whereas for electricity it can be 95, 99%. Additionally, internal combustion engines have a much greater mass than an electric motor. For instance, the Tesla has a motor that's 70 pounds. You could hold it in your hands. So we compared the Lotus Elise to the Tesla Roadster. They're made from the same frame, almost identical cars, well, except this is an internal combustion engine and this has an electric motor and a battery pack. We compared the mass of the drive system and we found that the internal combustion engine had a much greater mass than did the electric motor. The major amount of mass is carried in the batteries, but you can determine how much batteries you have, so your electric motor system could have less mass or more mass than your internal combustion engine depending on what range you wanted, how far you needed to drive. The same result was found when we compared the cost of driving an electric car with the cost of driving an internal combustion engine. The major cost for an electric car is in the range that you want. If you don't need to drive 400 kilometers, your electric car is going to cost you considerably less to drive than an internal combustion engine. And the question is, how far do you need to drive? It turns out that we don't need to drive 400 kilometers or about 250 miles. We can see here well over 90% of our trips are 90 miles or less. This is driving habits of an American. Additionally, if we can charge our car wherever we go, then we can see that 99% of our trips are 90 miles or less. So an electric car is fine as long as we don't need to drive very far. If you need to drive very far, there are a number of other ways you could do it. You could take public transport, you could borrow a friend's car, or you could drive your other car because Californians, for instance, would have 5 or 6 or 7 cars. So battery electric vehicles actually have a very good energy density compared to that of internal combustion engines. They have lower life cycle costs, but if you need a large range, if you need to drive very far, you're going to want an internal combustion engine. Technological improvements are presently improving for the battery electric vehicle. And we presently have a number of battery electric vehicles that can drive a moderate range. So what if we had more charging stations and we could keep this large distribution of battery electric storage connected to the grid as much as possible? It would do two things. It would increase the range that you could drive with your car. It could also use the cars as a dispatchable load and an electricity storage device. So not only would this be great for the cars because they could drive further, but it would help stabilize the grid because you could actually pull some energy from the cars during the day if you needed it. For instance, if you had a large solar electric facility and the clouds came over it and it dropped its production. Electric motors have a very high torque at low RPMs, unlike gasoline engines, and so you can get really good performance from them. The EV1, for instance, was not a muscle car. It was an economy car. This is the car in Who Killed the Electric Car, GM's electric car that they destroyed. So it's just an economy car. And we can see how it stacks up against these two sports cars, the Mazda Miata, how it pulls ahead. And it pulls ahead at a crucial point when the two other cars have to switch gears because an electric motor has a wide range over which it can provide high torque. So you don't need gears. An interesting resource that now becomes very important is lithium for the lithium-ion batteries, and it turns out that half of the world's lithium is in Bolivia. Bolivia is a very left-leaning country. The United States does not have a good relationship with Bolivia, and so we have a similar situation to Arab oil countries that we don't get along with.